Hello guys. This video I'm doing deals with a little bit about coils. It's mainly from a video of someone I subscribed to. I kind of told him that I'd probably be making a video on this a little bit. The biggest thing about it, the thing I want to talk about it more than anything is the resistance of coils and what you do about it if you rewind one and it's not quite the same, and does it matter and what's going on. So we need to express a little terminology. You have a coil in a tank circuit, say it can be your antenna coil, and there's your tuning condenser here. It could be an oscillator coil, whatever. The coil has inherent amount of resistance in it. It's made of wire. Wire has resistance, and that's one quick way of checking a coil to make sure it's all right. A lot of schematics have resistances on them, values, and you just take your own meter and check the coil and see if it matches. Well, that resistance is, and generally it's R sub S. It's known as series resistance is the true name of it, but it can be represented as just a resistor on in a circuit. Now, one of the things that can happen, let's say you got a coil, and I don't know, say an antenna coil for example, and it's open. It's got a bad winding in it, and it's deep inside. Sometimes coils can have a break just right at the very end, one end, where you can just kind of clean it up a little bit. Maybe you might have to attach a little bit of wire to it, but resolder it back on. A lot of other coils, unfortunately, are somewhere in the middle of the coil someplace. It's broke. May even have 2 or 3 breaks. So, in any case, you're going to have to rewind the coil. Now, this is not, I'm not going to be discussing about, I've already made a video or two about how to determine the number of turns and how to figure out the number of turns you need for a given inductance that you might need. I went over in past videos over to how to even find out what that inductance needs to be for a tank circuit for a resonant frequency and such. Now, what we're going to talk about is you already know what you need. So you're already set up to wind a new coil. And so you get some new magnet wire and everything, and you wind a new coil. And when you're done, say the inductance is off. You did everything right, you thought, and the resistance is off. Well, the inductance you can adjust by adjusting your turns. Okay, that's not a problem. You get it correct. But maybe the resistance is still off. Well, let's talk about a little bit why the resistance may be off. You may be working on something that is, from the 30s, 40s, and back in those days when they made wire, there's 3 things that went on in the process of, say, magnet wire, okay, insulated wire for coils. Number one, the purity of the copper wasn't near as what it is today. Today we can generally get, average magnet wire runs between 97.5% to 99% pure copper. So there's very few impurities in it that can cause problems with it being off resistance or anything. The second thing is, back in the day, theirs was usually more in the range of the 60s, upper 60% to low 70% pure copper. The other thing that they ran into is back then when they extruded wire, when you make wire, you actually take a chunk of metal, in this case copper, and you start pulling it through what they call an extrusion die, and you keep increasingly getting it smaller and smaller until you get to the size that you want. Okay, you heat the wire slightly to make it a little more malleable, but and you use lubrication and everything else, but you just keep pulling it and pulling it and pulling it until you get to the size, going through dies that are smaller and smaller and smaller until you get to the size that you want. Well, back in the day, they didn't have computers, and they didn't have computer controls, and they didn't have anything like that, so their extrusions weren't near as good as it is today. Generally, any length of wire today, you could take, feet, meters, yards of it, whatever, long lengths of it, and today's wire, and measure it. You methodically go in there and accurately measure that wire throughout that entire distance, and you'll find that it varies very little. But back in the day, it could vary as much as 30%. The other thing was the coating that they put on it also varied quite a bit. It was adequate. It wasn't like it might short, but it could go from a thicker to a thinner to a thicker, and back and forth, as much as 20 to 30%. And all this adds up to a wire that had a higher resistance for any length compared to today's wire. And when it was made into a coil, it could change slightly the dimensions from the mathematical formula, which meant that they had to adjust the coil to finalize it to its inductance. And once they got that figured out, they knew exactly how to mass produce at that, but it won't exactly match the theoretical or the mathematical model. And so if you go rewinding one in accordantly, it may be a little different, slight differences in inductance, but more importantly, I have a difference in resistance. Now, why is that important or not important? And I'm here to tell you it's not important what the resistance is, at least as far as the tank circuit is concerned, as far as the resonant frequency. The resistor amounts to nothing as far as the series resistance. That resistance in that coil matters none as far as the resonant frequency in the tank circuit. The other consideration would be the total impedance of the tank circuit. And basically what impedance is which is represented by Z. It's a square root problem. You have X sub L and X sub C. These are your inductive reactances measured in ohms. And inductive reactance is 2 pi frequency times the inductance of the inductor, and X sub C, which is in capacitive reactance, is 1 over 2 pi frequency times capacitance. Both are, which I didn't have that on there, both are in ohms. Well, you take these two, square each one, add them together. Now there's the series resistance, you take plus it squared, and that gives you the total impedance. Now, I had done just off camera a little math, and I just picked some numbers. 20 ohms for the series, which is pretty big. Most coils aren't never going to be quite that big, at least not in broadcast radio or something like that. But we'll just use 20. And we took 1,000 ohms for each of our reactances. When you work out the math, it comes out to 1,414.35. If I take that series resistance out, do the problem again, it comes out to 1414.21. A difference of 0.14 not having that 20 ohms in there. So you can see that really it makes no difference. And its size, if it was half the size, it would be somewhere in between if you put it in the formula. In fact, normal procedure when you're figuring out the impedance of a tank circuit like this, you just forget the series resistance entirely. You don't even figure it in the problem. Now, where does that resistance matter? Well, it matters with something called Q, or quality of the coil. And Q equals X sub L, the inductive reactance, over the series resistance. Now, you want Q to be fairly high, but the thing is, the higher Q gets, the narrower the bandwidth gets. In other words, if you looked at the bandwidth of a coil and say it was like this, at a certain Q, a low Q, if you increase the bandwidth or increase the Q, you may get something more like this. The bandwidth gets narrower, you get more passage through and more energy through. So lower the Q, it kind of attenuates the signal, but it also is wider bandwidth. Now, on an antenna circuit, you're going to want a somewhat of a wider bandwidth than what you might normally think. And the main reason is something I haven't talked about yet, and I'll have to do in one of the theory videos, talk more deeper into it, is sidebands. You have your carrier frequency, and then you have two sidebands, the upper and the lower sideband. The sidebands is your audio. That's what they are. The upper sidebands, the higher frequency audio frequencies, the lower sidebands, the lower ones. If you get the bandwidth too narrow, you start cutting off those sidebands. So you want to keep it, in a certain reasonable size. Now, if you already pretty well know what the proper inductance was supposed to be for your tank circuit, say an antenna, which you had to either figure something in order to wind a new coil, and you know what your capacitance is, you can measure it without any problem, and you know what the schematic said for the resistance on that coil, which will be your series resistance. You can figure out the Q of the way it was designed originally. If your new coil is low enough in resistance for the same inductance that it has drastically, changed that Q where you're uncomfortable with it, you don't know if it's going to work, then you can add, in series, an extra resistor. It will not change anything other than the Q. But you can add a resistor in here as long as it's just in series with the inductor or the coil, and those both are in parallel with your capacitor. It'll be a small value, because most of these coils run like 6-8 ohms. So if you was off, say you was only like 4 ohms on your coil after you got done, you could add a little 2 ohm resistor in there just to bring that Q back into something that is more probably what it should have been. But that's all you got to do, just add a series resistor in, and that takes care of it. Now that's about all I'm going to say on this. The big point was, don't get really concerned about the resistor. Worry about your inductance. Make sure it's correct, because that's what's going to be setting your resonant frequency. You get it off too much, you won't have any adjustment in any of your patters or trimmers to get the radio line. So then it won't be working properly for you. So you want to make sure you get it correct. Get the inductance correct. As far as resistance goes, the worst case scenario, it's going to be low. And if you need to, you can add a extra resistor in there. It won't do anything more than adjust that Q for you. Now, I did get the SAM service folders put up. and they're up there. I suggest you go read through them because there's some interesting stuff on them, and that you might find quite interesting. One thing that Sam's did back in the day, now I don't know if they still do or not, but they wanted to get, at least in the early days, they wanted to get what they called field experiences. They wanted to hear from the service techs, or as they call them, service engineers, which is really more the proper term. They wanted to hear from them, you know, about problems that, you know, things that they ran into working on radios in their years of working on them. And if they published them, then they would get, for each time each one they published, they would get a full SAMS folder that was coming out next, free of charge. And then the folder can contain quite a few sets in it, number several schematics. So, for, you know, if they published it for you. And I wanted to kind of go through some of these just to point out some, well, more or less to show you that, you know, I may not be the only one that ever runs into weird problems, and tell you why I told you to never trust anything. And also kind of show you what a lot of these guys were doing back in the day. And most of these are dated like 46 and 47, so that kind of gives you some example of the age. One interesting one here is, it's on a Farnsworth ETO-60, ETO-61, and ETO-63, those models. If you have distorted and weak on all but local stations when first turned on, clears up in about an hour, then what most likely was going on, and what they found, was leakage from the primary to the secondary coils in the second IF transformer. Now, I don't have any transformers here, but I'm sure you've seen those taken apart before. I've showed some before. But they're on a coil form, and there's two coils on there with a little distance separating them. And evidently these, at least on the Farnsworth, and it may run into some other radios, but that kind of problem ended up being a slight leakage between the two coils. Now, I don't know if it was the wires themselves as they go down and hook into the connections, you know, from the coils where they're soldered on, or if it was actually leakage bleeding down through the form. But in any case, leakage. Of course, they just replaced the IF transformer. Let's see here. Okay. Here's an interesting one, and this might be of interest especially to, well, to about anybody, but also yeah, to anybody also who paints a chassis, to be careful of. But this isn't on a painted chassis. This would be, you know, the chassis in good shape. This is on a Fada 1000 series. The complaint was set howls from 800 kc to 550 kc. They've had this trouble in 3 different sets, and it could be cured by detuning the IF trimmers. In other words, unaligning the sets, which is not a good idea. And they say that, but the sets would be broad tuning and lack sensitivity, so that wasn't a good answer, but at least it was something that would show up how one way of at least determining the problem a little more. What it turned out for them to fix it was they took and turned a turn and a half on the nuts that hold the second IF to the chassis, cleared up the trouble. They said, incidentally, these nuts appeared to be tight, but not tight enough because these extra turns really did the job. And what was going on was they just weren't grounding. The cans weren't grounding. Those cans have to ground. They're a shield. And they had to turn it 1.5 turns just to tighten it up enough to get a good ground going for whatever reasons. I'm not sure why. But if you paint your chassis, keep that in mind to make sure that those cans get tightened good and they're getting good ground. Because if not, you may end up, it don't have to be a Fada, it can be any radio, you may end up some feedback. And yeah, and if you do get that, and if you find if you just kind of turn the screws on there and it goes away, then it's probably the IF can. Let's see, complaint recovery, receiver noise. This receiver played normally at some time, for some time, but occasionally developed a long or a loud noise similar to that of a noisy 35Z5 GT tube, which is 35Z5 is a rectifier tube. Any attempt to trace noise would cause it to disappear for varying periods of time. Filter condenser tested good. However, the installation of a new 3-section condenser eliminated the noise. Now, here's something, the reason why I picked this one out was they would have been using, when they tested that, if I can get up here, a tester like this. Okay, this is, you've seen it before, it's my Coil 950B. Not, you know, it's a bridge, yeah, keep it on there, that'd be smart. You not only check for capacitance, but see, when they did their test, they would also check it for leakage down here by turning the knob when it's on leakage, and this one goes up to over 500 volts. So they would have checked it that way and checked that condenser and found it to be good, yet they eliminated the noise after replacing it. So a condenser could check good, check both capacitance, it's good, leakage, has no leakage, and still can cause a problem. Just something to think about. Let's see here. Okay, this was an interesting one, I thought. It was on an Emerson 505 model. It was inoperative, but it showed positive voltage on RF grids and the AVC circuit. In other words, the AVC circuit was showing positive voltage instead of negative like it's supposed to. Check for shorted wires in IF coil cans. We have found several where the grid wires were laid across the high voltage terminals and the insulation broke down after a short period of use. This would apply to any set. Now what they're talking about, if you see it inside an IF can, and like I said, I've had videos on them, other people have, but there's real fine wires coming from the coils and they go down or up to the top of the can or something, but they go to a point where they're soldered on, and then your main wires coming in solder them points, those lugs. And I've seen several of these where the wires actually did cross, and a lot of times they can cross. They're supposed, you know, they're insulated, but if that insulation breaks down, it could possibly cause a problem. So if you ever have a problem like this, that might be worth investigating. Pull the cans apart, you know, take the IFs out, pull the cans, pull them out of the cans, and look at those wires. Make sure that they're, if they are crossed, they're not shorting out. Let's see. All right, let's see. Alright, here's one. It's on a RCA model 56X. There's actually several of them here, but I'm going to read the last one. Says that everything checks okay, but set still won't operate. They tried changing the 12J5 tube. This tube checked good and still wouldn't oscillate. When they changed the tube, it worked. Even though the tube checked good, it still wouldn't work and oscillate. 12J5 it's just a triode. It's the same thing as 6J5, uses an oscillator a lot of times. In this case, they had a good checking tube, but would not oscillate. Changed it, and the radio started working. Let's see. Okay, anyway, next. Okay, let's see. What's this one? Okay, this one was rather, I think this is the one that's rather interesting. So Electronic Lab Model 2701. They say they would like to pass along the experiences. Anyway, the set Model 2701, they noticed that the set hummed as if the filter network were faulty, but a check showed that the fault was elsewhere. Replacing the 35L6 audio output tube cured the trouble. I would recommend replacement of this tube before making further checks on this particular model for excessive hum. It's not the one I was thinking of. Oh, okay, yeah, it is. They recommend the replacement of this tube without any further checks. I just didn't read it far enough. The tube that they removed from the above set checked okay. It looked good on the tube tester, checked good. The interesting thing is it worked well in another set as well. And I assume, I'm making an assumption here, when they met another set, a total different make and model radio, but in this radio there was something about that tube. Maybe the internal capacitance had changed, maybe it had some slight leakage in it that wouldn't show up on their tester and most testers, or something going on with it that radio was picky enough it wouldn't work. So it would work, but it'd cause hum. So sometimes tubes may check good and still have problems with them. They still may not function properly or not function at all. The radio can be dead even though the tubes check good. The only real test for any tube is in service. Let's see, a Farnsworth ETO 60, ETO 61, and ETO 63, distorted and weak on all but local stations when first turned on, clears up in about an hour. Trouble found to be leakage, again from primary to secondary of the second IF transformer. That was a total different one. Let's see. Let's see. In testing one set, there was no plate voltage on the 1H5 tube. This would be like a battery operated or AC/DC set. The plate lead used for the number 8 pin of the 1N5, okay, the plate lead for the 1H5 was wired to the pin number 8 on the 1N5, which has no internal connection but was used as just a junction point. So in other words, the 1N5 normally has nothing connected to pin 8. So they could use that, and a lot of radio manufacturers do. They'll use unused socket pins on the sockets as tie points. Although the 1N5 tested good, I discovered that its number 8 pin was shorted internally to the shell and thus grounding the plate of the 1H5. So another tube that tested good, and yet it was had an internal short that the tube tester probably would never pick up on, because when you set them, a lot of times they're set up so that the manufacturer of the tube tester and everybody knows that that pin 8 probably wouldn't be internally connected, so there's no use in making any connections to it as far as when you're setting your switches and everything. Let's see. Okay, an Air King model 4625. In record players like the Air King model 4625, the 12SQ7 or 14B6 may become microphonic after a few hundred hours of use. This is caused by the diode plates becoming loose from vibration. The tube will check OK on the meter. The cure, connect the diode plates to the cathode or to the ground. Now, obviously what they're doing with this particular tube in this record player is they're using just as a preamp. Just the triode section of the 12SQ7, which is a dual diode triode. And so they didn't need the diodes. It's not doing any detection, so, and they left them open. Now a lot of manufacturers will go ahead and ground those. Evidently the Air King did not, and they found after use those would start vibrating, and which cause microphonics inside the tube, and you pick that up here in the speaker. So they just connected them to ground, ended that. Now I only covered just very few of those. This video is getting extremely long. I'm sorry about that. The thing is, check them out. A lot of good information in here, and these are from people, you know, just people out there that ran businesses and worked on radios and TVs, and this you know, this was some of their experiences that they've ran into. And got published in SAMS, so it's an interesting read. So anyway, I'm not even sure what I'm going to call this video. I'll figure out a name for it. But I want to thank you for watching. I want to give you some heads up on what's coming up. I will make another video of the other radio that I've been working on. One thing that I'm going to be doing is starting a little series also amongst the other series I got to keep working on. There's going to be a math video coming up. It's going to be Introduction to Trig. But the other series is going to be literally going over reading schematics. We're going to start at the front end. We're going to look at a schematic. We're going to look at every component in each section, each stage. Go over what that component's there for, why they're, you know, why it's there and everything, and how it operates and what it pertains to the operation of that section or stage radio, what happens if it goes bad, and so on, as we go through it, so that you can understand a schematic much better and stuff. It's not going to be something like I've done a few already on how to find, you know, where's this capacitor at in the radio, where's this resistor at in the radio, and stuff. We've talked about that before. This is going to be pure schematic reading and understanding. So that'll be coming up soon. So anyway, thanks for watching and your comments and stuff, and I'll see you on the next video.